I'll talk about that. Well, I think we have about 15 seconds until 7. So we'll start at 7. Let's see if I've got that up. Oh, yes, I do. Oh, Abby is here. Lily, Mika. It's a good group. Well, I would like to sort of start on time if we can. So if you would open that file, and for a minute I'm going to share, but I will unshare in a few minutes. So you should be seeing it now, I hope. And the first problem is you have a solid region that lies between the two graphs that I gave, z equals 3x squared plus y plus 1, and z equals 0, and above the rectangle where x is between 1 and 3, and y is between 0 and 4. Plot the region. So there are a few things to deal with immediately. It's between these two graphs, and you should find out which one is on top. And this one's kind of a giveaway because z equals 0 is in 1, and the other one primarily lies above the z is positive. X squared is always positive. There are some places where it's negative because y can be negative. But over that rectangle, this is entirely positive. So here I define, let's see, this is getting in the way a little bit, but here we define D1, and this is just a little rectangular region over which this thing lies. So I did that because this could be a region over which we integrate. So this can become handy, and so I did that immediately, recognizing that it was a place we could integrate over. D2 is actually the region. So this is the entire region, and it's defined exactly by the conditions that I gave in that sentence. X is between 1 and 3, y is between 0 and 4, and z lies somewhere between 0 and the paraboloid that's above it. So there are a couple ways to look at this, and I indicated discretize region and region. Here I have the regions are uncommented. I don't have semicolons behind them. And that is because these use much less computing power, and you don't want your Mathematica logging down while you do the exam. So here are the plots, and I actually didn't ask you for a plot of D1, so I could comment that out, but I wanted that defined. So there is a plot of the actual region that we're talking about. You can't do much with this plot because region it just provides you with one view. Discretize is much better if you want to investigate it. But if I only ask you to plot it, this is what I did. By the way, interrupt me at any time if you have questions. So this is the first thing we had to do, is to plot that region. And the second thing is to compute the volume. So that's the second thing we want to do here. Compute the volume of R. And there are lots of ways to do this. And here are some ways that I picked out. Here I defined the function f of x and y. And so we can integrate this function over the base, which is D1, and that should give the volume under the graph. Or we could integrate over and just specify, this is now, the first one is a double integral. This one is an iterated integral, where first we're integrating with respect to, I think, with respect to x, and then with respect to y over this rectangular region. The third one is just basically integrating the one function over the region. And by the region in this case, I mean the entire region, D2, the one we plotted. I was going to do another one, it looks like, but I didn't. We'll get rid of that guy. So let's see what these look like. Oh yeah, 128. So they all give the same value. 128. So that's the volume that we've got here. And any of those methods work. Again, I'm rolling along, but interrupt me whenever you've got questions. Compute the moment of r in the z direction. Now, I think these moments, I set up these moments using sort of that third method, integrating over the entire region. So if you want the moment in the x direction, you integrate x. If you want the moment in the y direction, you integrate y. If you want the volume, you integrate 1. If you want the moment in the z direction, you integrate z. And so these are triple integrals that we're doing because we've got 3 variables. And you can do these as double integrals. The one with z is a little tricky to do as a double integral or as an iterated integral. The other 2 are pretty easy because you're integrating over a domain D1 that has x's and y's defined with x's and y's. But the easiest way to do it, I think, is the definition of these moments integrating either x, y, or z over the entire region. So let's see what we get here. So for these, you integrate, so the moment in the x direction is 288, the moment in the y direction is 266.7, and the moment in the z direction is 1,224.5. So these moments are good for computing centers. These are called the first moments. The second, if you wanted to compute the second moments, the polar moments, there would be the second moment, or the moment of inertia in the x direction and in the y direction and so on. You integrate x squared. So
wait, so the moment and the moment of inertia are different things?
Absolutely. The moment is called the first moment because you're integrating x to the 1 power. If you're looking for moment of inertia, you're going to integrate x squared. And moment of inertia in each of the directions is integrating it's called the second moment. Statistics calls these by first moment, second moment, third moment. Physics and a good deal of mathematics calls them moment and moment of inertia and quits there. Statistics uses a lot more. They use third and fourth moments also. They know what they're doing too. They've got some pretty good results involving these things like central limit theorem. All right. So now in the next one here, we ask you to use these. How do you compute the center? The center of this, there is no, I didn't give a density. So we're not talking mass here. We're talking the geometric center of these objects, or you could think of it as having the density as being a constant throughout the object and finding the center. And the answer to that is you just divide each of the moments by, you divide each of the moments by the measure involved, which in this case is volume. So if you look at the x coordinate of the center is the x moment over the volume. Y moment, moment in the y direction over the volume, moment in the z direction over the volume. And we see what those are, maybe. Two and a quarter, about 2.1, about 9 and 9.6, something like that. So that is a three-dimensional balance point of that object.
Professor Homke, I have a question. How would computing the center change if the density varies over the region?
So it then it changes. So let's do one like that. I think we can. I will just work here. Where did we find the? Oh, here we're integrating. So what would you like the density to be? It'll depend on x, y, and z, and it'll just be a real valued function. What would you like it to be, Abby? It could be anything.
Like x squared plus y squared plus xz.
Okay, so then instead of x squared plus y squared plus xz. So now we're going to integrate the.
I think you forgot to type the y squared.
Who's the prof here, Jasmine? Oh yeah, I did. Okay, yes. So you integrate the density, and now you're going to get a mass. So density is mass per unit volume. So now we're going to get a measure of how much physical existence this object has in total. How much physical existence does it have? And we integrate, and now we get a bigger number. I only did this with the last one here. But now we get this number. And now when we integrate these, instead of integrating just x, we're going to integrate x times the density. So x star density. And we need another, there we go. And then y star density and z star density. Does this make sense what I'm doing here, Abby?
Yeah, that makes a lot of sense.
Yeah, x times the density, so that it makes it more complicated. But again, this integration technique works pretty well. It doesn't give exact answers, but it gives you the idea of what these are. If you wanted more accuracy, then you can request it. There are ways to request it. We can request it here, but I don't want to get into that. This has to do with, we don't need that. We just need to know how these work. And then with the center, compute the center. Here I didn't, here this is the moment in the x direction divided by the measure, but everything has changed now. The moment in the x direction is now 10,860. And the measure is no longer 128, it's 4,397. It's the mass. What did I say? 4,397. So this will just give, so that shifted the center of mass in the x direction some. I forget what it was before, 2.25, I think. Now it's a little bigger. And it was your density function that did it, Abby. You are to blame for this. Does this make sense here?
Yeah, it does.
Yeah, the geometric center is very interesting, but often it's not exactly what you want. If you have an object that's made out of layers of material or a complicated object, then you want to use the mass density. Other questions? Shall we move on?
Can you say again, how do we find the new mass? So after the density is not 1, so do we just do the integral?
Yeah, that's what I did up above
Okay.
here.
Okay.
I forget where I did it.
Okay.
Oh,
That
here I
makes
did it
sense.
in the very last one here.
Mhm.
I integrated Abby's density. So if you integrate the density function, which is x squared plus y squared plus xz, and you integrate it over the same object, now it will not give you the volume. Now it gives you the total mass that's there.
Okay, that makes sense.
And we could have done it these other ways as well. This middle way, where we're integrating the function of x and y, this doesn't work very well. This doesn't work as well for finding the for that integral is not exactly what we want. And the same thing for moment in the z direction. In fact, moment in the z direction is hard to do that way. It takes a little, it's a little trickier. Shall we move on? The first one that's, I think, somewhat exciting is the parameterization of the top of a piece of this thing. Find a parametric function whose graph is the top. A parameterization of a geometric object means a function whose range is that object. And we want that function to be as close to 1-to-1 as possible. This is the top of an object in the z sense, and so is a piece of the graph. So this is a piece of the graph of 3x squared plus y plus 1, and it's a piece of the graph that is excised by this rectangular domain that we have. So if you think of the entire graph and then excise it, y between, what was it, 0 and 4, and x between 1 and 3, the piece of the graph that's left after cutting away those exterior pieces is what we're looking at. And so here I chose to use the graph parameterization, meaning the two of your variables are the x and the y. And so here I used an s and a t. So u of s and t is s and t. And so s will go between, s is the x, so it goes between 1 and 3, and t will go between 0 and 4. So this is a very good thing for integration. And this is the 3x squared plus y plus 1 with the s and the t plugged in. So this is the so-called graph parameterization. And it means, and for us, we're interested in s's and t's in that rectangular base that I labeled D1 earlier. So then we're supposed to find, I think we're supposed to find u prime of s and t. So I did it by hand here. It's a 3x2 matrix. So here we have an X coordinate, a Y coordinate, and a Z coordinate. Those are going to be the rows. The columns are the S column and the T column, representing the two variables that we have. And so this 1 is the partial of this S with respect to this S. The partial of S with respect to T is 0. Then working on the second coordinate, T, the derivative of it with respect to S is 0. The derivative of it with respect to T is 1. And now the Z coordinate, that's this last row. The derivative with respect to S is 6S. The derivative with respect to T is 1. That's the derivative. In some way or another, all of these things are going to be asked. I mean, I want you to know this stuff. So, and it's easy to ask, so it is likely. So let's see what is next. Set up an integral which, if evaluated, would give the surface area of the top of this region. And so there it is. We're going to integrate the one function times the expansion contraction factor. S is between 1 and 3. T is between 0 and 4. And you get the expansion contraction factor by taking the sum of the squares of the 2x2 determinants that are contained in here. The top determinant, can you see this little marker when I indicate a little circular area? Okay, so that 2x2 determinant is 1 times 1, or 1. That's the first one down here in the square root. The next determinant is the top, is the bottom 4. So the determinant there is minus 6x, and when you square it, you get 36s squared. And then the last one is the top row and the last row. That determinant is 1, and when we square it, we get 1. So the whole expansion contraction factor is the square root of 2 plus 36s squared. We integrate that between 1 and 3 in the S direction, 0 and 4 in the Y direction, and we get some crazy number, 96.7. So that would be square feet if this is in feet, or it's square units. This is an area measurement. And so ends problem 1. How did this go? How did you do on problem 1? Lauren, thumbs up. Asa, thumbs up. Lily, I'm sure it's thumbs up, but I can't see you in there. Riley, how'd this go for you? Are you there?
Yeah, but it was good for me.
Any questions about this? All right. Let's take a look at problem 2. Maximize and minimize. Is this the one I gave you, 2x squared? I don't think it is. Oh, bummer.
I think you have it right in the code though.
Oh yeah, I do. I'm going to put that in here. Okay. So this is make that change in yours. So this is the function that we want to maximize and minimize. And D is the region over which we want to maximize it and minimize it. And this is not right either. Is this, this should be 4x squared. That is right in the code though, plus 9y squared. Less than or equal to 36. Okay. And y is greater than 2x, or is it 3x? I forget. Hang on for just a second here.
You only listed the 4x squared plus 9y squared less than or equal to 36. That's all you gave us.
Oh, that's all I gave you. Okay, so that's
Yeah.
good. So this probably came from last year's stuff. But anyway, here we go. And once I get the problem straight, then I'd like you to compute the first two derivatives. So we have to enter the function. Here it is. I entered the region right away because this is the region that we're going to be interested in. This is the domain of the function. And so this is all the background material. Then F1 is the first derivative. And I just did it by hand. I mean, you could do this with Mathematica code, but it's a polynomial, so I just did it by hand. Hopefully it's correct. And then the second derivative I also did by hand. So this is a 2x2 derivative. The upper left is the derivative of the first. It's the second partial with respect to x. So it's 24x squared. And then the one to the right of that is the partial with respect to x, and then the partial with respect to y. So that's -4. Lower left is -4. That's the partial with respect to y, then the partial with respect to x. Except under the circumstances that we have, those two diagonals, the main diagonal elements will always be equal. They don't actually have to be, but if the second derivatives are continuous, they will be. And then the last one, the lower right, is the second derivative of f with respect to y, 12y squared. So this is a matrix. And so this just gives us the background and computed a couple things that we will need. And now find and classify the critical points. So let's take a look at that. So here I'm going to solve for the critical points by taking the derivative, setting it equal to 0, and solving. And I'm only going to look for the solutions that are in D3. So I used a little Mathematica code to solve. Actually, you can solve these by hand. They're not impossible to solve by hand. But it's easy enough to do this.
Can you just set it equal to 0 and then like visually see which ones are in D3, or do you want the code like within D3?
Let's just take a look. So I must not have entered something here.
I'm just saying that like if you just set the derivative equal to 0, you get probably a set of 10 to 12 points. But can you just like knowing what D3 is, can you just visually say discard? Okay, all of these are out of the region. These are the ones that actually matter.
You can, but if you use the code that I give you, it spits out the ones that are just in D3. So if you don't specify that, suppose I just wanted the real solutions. I guess maybe there are there only, I think that's not right. I thought there were more, but maybe there aren't. Maybe this is all of them.
Yeah, that's all of the real ones. The
Okay.
rest-
But this, if you put it in D3, it'll kick out all of the complex ones if there are any, and give the ones that are only in D3, or you can pick them out by hand if you want. If your region is tricky, it can be a little tricky to see which ones are in and which ones aren't. And then what I computed down here is the determinant of, I got these, and then I looked at the Hessian determinant with those values plugged in. And I got a -16 for 0, 0. That means that 0, 0 is a saddle point. And then I got 128 something, a positive number for the other ones. That means that they are either maxes or mins. And then I should have plugged those into the first derivative to see if they are maxes or mins. So maybe let's do that. So actually, we want to look at either fxx or fyy. So 24x squared, and these are the concavity terms. So this is always positive, and this one's always positive. So these are always concave up. And this 128 says that even that there is a consistency, that concavity is consistent, is what this is telling you. This tells you concavity is inconsistent at 0, 0. So sometimes it's up and sometimes it's down. That's why it's a saddle point. These two tell you the other 2 points, the concavity is consistent and the concavity is positive. So these are both minima. Oh, that's the parameterization of the boundary. This is the one I wanted. So 0, 0 is a saddle point. The other two are local mins. Now, the first interesting thing is to find a parameterization for the boundary. So I thought I'd defined this before, but anyway, here is the implicit region. And now we're going to take a look at that region.
Question about the implicit region. Is there a reason that you put curly brackets for the D3 but didn't have curly brackets for the D2? Is there like a difference when defining implicit region?
No, I should have had curly brackets for D2 too.
Okay, so it's standard to use the curly brackets.
Yeah, D2 has them here. The curly brackets are around.
I mean your D3 that, oh, okay, maybe this is problem. The D3 you defined in problem 2. Oh yeah, problem 2, sorry.
All right, let's go back.
Right there.
Oh, right here. Yeah,
Yeah.
I guess it did it with or without. In general, there are more than one constraint. This is just one constraint. So maybe I got away with something there. Is this Lauren who asked me?
Yeah, I wasn't sure which way was standard. But
I think
that's
standard
good.
is you put the braces. It expects,
Perfect. Thank you.
so maybe I was lucky. But now we're going to look at the region. I'll take out this semicolon. We'll take a look at it. So there it is. It's an ellipse. And here is the equation for the ellipse. I used a polar coordinates type thing here. And here I did it again. Oh, this is just the output from implicit region because I didn't have a semicolon. But R of t is this. This exactly describes the boundary of that ellipse, where R goes between, or where the boundary of the ellipse that we have, x radius 3, y radius 2.
Should it?
Isn't it?
why-
Yeah,
Is it the other way?
they should be switched around.
2 and 3 is the x radius 2.
Yeah, because it's 4x squared plus 9y squared is less than
Oh, no,
36.
no. I was too quick. Because it's less than 36. So to see what the radii, so to see what the radii are, I forget what we have. 9x squared plus 4y squared.
4x squared plus 9y squared.
Yeah, you just have to switch the two. It's easy.
Oh, really?
Well, no, you just switch it. It's 2 cosine of t, 3 sine of t. He had it the opposite way.
No, but that's not it. Wait. This x radius is not 2. You have to put these in standard form in order to find the radius.
Divide by 36.
So you need to divide by the 36.
Oh, so it's square root 6.
So you need to divide by the 36, and you need to do a little arithmetic. So this is x squared over 9 plus y squared over 4 less than or equal to 1. Now you can read the radii. This is how you read the radii. This is the standard form of an ellipse equation.
Could you move the camera up a little bit, Professor, please?
Yeah, sure.
Thank you very much.
It was my pleasure. I wish I wouldn't forget that all the time, but that's life. So this is the standard form. You set these less than or equal to 1, then you can read off the radii. So the x radius is 3, the y radius is 2.
Yeah, you just had it mixed up.
So I think that's what I had. I didn't have that? Okay, we'll change it. All right, well, let's see. So that will, the x radius. Yeah, x radius is 3, y radius is 2. It should be what I've got right here. This describes that equation. And I'm going to unshare again. To see that that's true, to see that those points satisfy the equation, sub in x equals 3 cosine t, y equals 2 sine t. No matter what t is, these two will make this equation true, actually equal to in our case. And let's just do it. 3 cosine t squared over 9 plus 2 sine t squared over 4. Computing this, you get 9 cos squared t over 9 plus 4 sine squared t over 4. Big old cancellations here. Sine squared plus cosine squared is 1. So the fact that you got 1, no matter what you put in for t, means that these 2 satisfy this equation independent of t, or it means for any t, these are on the equation. So this is a parameterization of this shape. And so this is the boundary. R describes the boundary. Let's see what we're going to do next. Maximize f on the boundary. I could have minimized f on the boundary too, but so f on boundary of t, f on boundary of t is f of this parameterization, f of r of t. I'm going to plot it. And then we will use n maximize, but plotting is good. So there is the plot. And so it appears that there are actually several points where the maximum occurs. It picked out the one that is 2 pi, that 6.24616 is 2 pi on the very right-hand side. But there's also one in the middle that is probably pi, and 0 also seems to give the same value. And the value is 164.44. So the maximum of f on the boundary is 164.44 occurring at 2 pi.
Professor?
Yep.
When I use your file and run it on my computer, it gives out a different result. I have like 28.037 at the maximum.
What do you have for the maximum?
28.037.
28.037. Actually, that sounds more reasonable.
Yeah, I use the same file that you have right now, and I run it, and it gives the different result.
That's too bad. My graph looks like it's above 160 also.
Oh, my graph is also different from you too.
Weird.
Yeah, I have the same thing.
Send me that file, Kang. We'll take a look.
Oh, it's the file on the Moodle that you upload.
It's the same file off of Moodle?
Yes. I can share the screen if you need it.
I think we should move on. I mean, this basic stuff, because I do have to quit at 8 because I have another one at 8:15. And
yes.
And unfortunately, no, we're good to go. And I have to download this video between. So let's look at problem 3 a little bit, and maybe a little bit problem 4. G is the solid region between these two graphs and inside this cylinder. Between these two graphs and inside this cylinder. So how would you do this? Well, it's between these graphs. So Z, if you're looking at implicit region, Z will be in between these, but you have to figure out which one is bigger and which one is smaller. So here again, there is a base defined in the XY plane. This is a circular base. The region is over that. G1 is the implicit region definition. And here we have it inside that x squared plus y squared less than 4 circle or disk. And then these two inequality signs here might go the other way. So you need to figure out which of the two expressions in X and Y is bigger than the other, the easiest way is to graph these, and I graphed them only at one point. You only have to check one point, basically. 0, 0 is in our G base region. If you check the left-hand side at 0, 0, you get -1. If you check the right-hand side, you get 1. So the right-hand equation is going to be bigger than the left-hand equation. And we're interested in the z's in between. So this is
the exam. Would you ever, if you were to give this problem on the exam, would you ever give regions that like crossed over each other so that like one was the top and then another one like became the top?
No, those are important questions actually, Asa, but I mean, it's sort of, if you do a little more multivariable calculus or use it, you're going to run into that situation. But that's complicated enough. We don't have time to deal with all these complications.
All right, cool. Thank you.
So the answer is no, but the answer in general is yes, it's important. But will it be on the test? No way, Hoser, not on the test, because it just too complicated for us right now. We're sort of interested in the basics. We want to find the volume. And again, there are billions of ways of finding the volume. So we can integrate the one function over the entire region, G1. Or we can integrate the difference between those functions over the base. Or we can set up an iterated integral to do it. And notice I didn't use n integrate there, I just used integrate. So that's going to give an exact answer using standard integration techniques. Oh, come on. Oh, I bet I didn't enter these. So it's working hard on integrating. There we go. So they all worked. (62.83, 62.8319, and 20 pi. Now 20 pi is the exact answer. So that answer is exact. It used exact techniques to do it. Wrote the answer in terms of pi. The other two are not quite the same because they're using approximation techniques, but close. Find the volume. Well, that's just what we found up above. If you did this in Cartesian coordinates, redo it in cylindrical coordinates.
Will you quick remind me on what the difference between cylindrical and spherical are?
Yep. So cylindrical coordinates are polar coordinates in two variables and the other variables left alone. So x, y, z equals in cylindrical coordinates r cosine theta, r sine theta, z. So this is.
So it's just polar in 3D, right?
This is one way to do polar in 3D. There are a couple ways to do polar in 3D. So this is a function of r, theta, and z. So this has its own expansion contraction factor, which ends up to be r. The other one, x, y, z, there are again several versions of this, but this is rho cosine theta sine phi, rho sine theta sine phi, comma, rho cosine phi. This is semi-standard. And in cylindrical coordinates, your polar line is the x-axis. Thetas are measured from the x-axis. And if you take a point here, the distance between this point and the origin, this line segment is r. And then z is what it always is. It's the height. So r, theta, z.
Thank you.
Spherical coordinates, a little different. You take a point here, x, y, z. And if you look at that point, the distance between it and the origin is rho. And then if you project that point down, this angle right here is theta. And if you look at the angle between the z-axis and this line, this depression angle is phi. So this is the kind of stuff you need in order to know what you're doing geometrically with these things. Set up an integral which gives the moment of the entire region about the x-axis. So in this case, we're going to integrate x over the entire region, G. G1 is what I call the entire region. It's the same thing. You integrate, rather than integrate 1 to get the volume, you integrate x to get the moment in the x. If you wanted to integrate, if you wanted the moment in the y direction, it would be this. Another way to do that is to integrate over your base. And if you take a vertical line in your object at some point xy in the base, that vertical line has length top minus bottom. If you multiply that by x and integrate, it will give you the same thing. Here is how to integrate using a triple integral and Cartesian coordinates. So this is an iterated integral, integrated x over the entire object. So the z goes between the bottom and the top. The y goes between the top and bottom of just the circle, x squared plus y squared less than or equal to 4. And then x runs the radii of that circle. All these give the exact same thing. I think I have to enter all of these to make it happen. And in the last one, we're actually finding, I'm integrating the last one. Let's see what we get here. Minus 12.56 or minus 4 pi. We're going to get to maybe problem 4. Parametric equations for the we did the moment in the x direction above. I computed it. Parametric functions for the top surface again. And again, I used the graph parameterization, st 3s squared plus t plus 1. Same functions we had before. S and t are in the base, or here it is in polar coordinates. r cosine t, this is cylindrical coordinates, I think. R cosine t, r sine t, and then 3x squared plus y plus 1. Notice that the x here is 3x squared. The x is the x. You don't use the variable x, you use what it's equal to, r cosine t. So that was squared. And the plus y, so plus r sine t plus 1. So here's the same thing using cylindrical coordinates. Or really, this is polar coordinates in the first two, and then z is what it is. Both of those will do it. Here is the same expansion contraction factor. So I worked out the expansion contraction factor just like in the first problem, integrated it, but this time the s's and t's were in this base, in this circular base.
Real quickly, is there a way to figure out the bounds of integration by using your parameterization, like doing a more iterated integral instead of doing it over a region?
Yeah, I mean, in these earlier ones, I actually did some of that. V is for R between, I mean, I think
Okay,
they're
so
actually here too. S2 is in the base. So I'm going to stop and just take a look at that here. The answer is yes. Let's take a look at that one. This integration is occurring over a circle of radius 2, a disk of radius 2 centered at the origin. So if we're going to do this as an integral, we're going to integrate over this. And let's integrate with respect to y first, and then integrate with respect to x. So what that means is that you're going to take an x value somewhere along the x-axis, and I guess -2 and 2 are going to delineate the x's, -2 and 2. That's where you're going to select the x's from. It's on the x-axis. So here's one, or here's one. And then the y, for this particular x, the y is going to range from the bottom of the disk up to the top. And the equation here is x squared plus y squared equals 2 for the boundary. And these are y values here. The bottom y value is minus the square root of 4 minus x squared. And the top value, the top y value at this x, is equal to the plus square root of 4 minus x squared. And so we have to fill in what we're going to put there, but this is how to integrate it. Lauren, is this okay?
Yes, thank you.
Yep. If you wanted to add in the z, I would do the z first, dz, dy, dx. And the integral of z would be between the bottom of this thing, which was, it's some linear function, I forget what it was, but the top I think is 3x squared plus y plus 1. And the bottom is, I don't know, something like, what was the bottom function? For
I
this
don't-
region?
It is x plus 2y minus 1.
Yeah, 3x is it, or
Just x. X plus 2y minus 1.
2y minus 1? Yeah. So there are the Cartesian limits for a triple integral.
Got it. Thank you.
Yep. let's just take a second and look at number 4, the asteroid. We're going to picture it. So the asteroid is the region between these two curves that I gave in terms of X's and Y's. It is all the X, Y, Z's between there. So this is easy to define in terms of implicit region, and we can take a look at it with region. If you do, you get this sort of thing, kind of looks like a blue whale here, or some kind of weird pill, but notice that it's got a ridge on it between those smooth surfaces, kind of as a top and a bottom, the way we're looking at it. So there are several things that might be interesting to find. So assuming this is the volume, how do you find the average temperature? Here is the first one here is the volume. You're integrating the 1 over the asteroid. This is the temperature function, I trust. It's got a $sign in there, which is a bad idea. So there is the temperature function, and we're going to integrate that. And then we're going to divide that by the volume. Let's see what we get. So the temperature, when we integrate the temperature over it, we get 0. The volume is a little more than 50, but the average temperature is 0 over this object. Here we do have a density function. And so here I ask you for the mass of it. So we're going to integrate that density function, 47 minus xyz over 10. And that will give us the total mass.
So for both mass and when finding the average temperature, you're integrating within the asteroid, like within the bounds of the asteroid. The bounds never change. You're always integrating within that region that you specified, correct?
Yeah, that's correct, because that's what we're interested in, the average temperature of the asteroid.
Okay, and that's when Z, okay.
And the mass of the asteroid. So it's the of the asteroid that affects this. Is this Meredith I'm talking to? No. Who was I talking to?
Yeah, it's Meredith.
Meredith, yeah. So yeah, it's the of the asteroid that is the key. So I did this because of what was asked. Actually, what is the mass of the asteroid, or what is the average temperature of the asteroid? And the asteroid is in some region, the region it occupies. So that's why we did that. I did another here. I don't know if you're interested, but the other is find the length of the ridge. If you're interested, you could look and see how I found that length of the ridge. I parameterized the ridge as a function of one variable. It's just a curve around that asteroid that we saw earlier. This little curve right there. And then I found its length by integrating the speed of the parameterization that I had. And the parameterization just came from the intersection of those two halves of it, the top half and the bottom half. Well, this has been a wild ride here tonight.